sense of the fish.
Okay, so the rest will have to be offline, and thank you again. Okay, and the next speaker, the last one. So the last speaker of this mini session is Jiang, and he's going to talk about the computation of correlated equilibrium.
Okay, thank you. So, this is joint work with my advisor, Kevin Nathan Brown. Oh, let's see if this works. Okay, in this talk, I'll first set up the computational problem of computing correlated equilibrium, and then I'll give an overview of Papadimitriou and Roughgarden's algorithm for computing correlated equilibrium, and briefly talk about certain numerical precision issues, which another group of researchers recently proposed that these numerical precision issues can prevent this algorithm from computing an exact solution. So finally, I'll present our main contribution, which is a modified version of the algorithm, which is able to compute the exact correlated equilibrium in polynomial time. So correlated equilibrium is a solution concept first proposed by, let me close. So this first proposed by Allman. To define it, we'll first introduce some notation. So we have a game with n players. Each player P has pure strategy SP from this action set. The pure strategy profile we write as S, and for each player P, each pure strategy profile, we have a utility for that player, which is assumed to be an integer. So there are several equivalent ways of defining correlated equilibrium. So we use the following definition. A correlated equilibrium, or CE, is a distribution over the set of pure strategy profiles such that if an intermediary draws a strategy profile from this distribution and reveal to each player her own component SP, then each player would have no incentive to deviate to a different strategy, assuming everyone else is following the suggestions. Mathematically, this can be written as a set of linear constraints. For each player P and each pair of actions ij of that player, we have the following incentive constraint. In fact, for this talk, we don't even have to care about the details of this, this expression. We can just write the set of incentive constraints as this expression ux greater or equal to 0. So there are a set of other constraints that make sure x is a probability distribution, and these constraints together defines the set of CE of the game. So this feasibility program has m to the n number of variables and n squared of constraints, where n is the max number of actions per player. So if the game is given in a normal form, this will be polynomial in size. However, the normal form is, we know, not a very efficient representation for games, especially for large games, because it grows exponentially in the number of players. So instead, we should look at more efficient representations. For games with structured utility functions, we can often represent the game more compactly, meaning using less number of bits. And there have been several such compact representations proposed in the literature, including symmetric games, anonymous games, graphical games, congestion games, action graph games. So I'm not going into details of each of them, but generally, given such a compactly represented game, we would like to compute a sample correlated equilibrium in time polynomial in the input size. So for this problem, we can see that the original LP approach wouldn't work because the size of the LP would be exponential for these inputs. And furthermore, to even write a solution would require exponential numbers. So now we introduce Papadimitriou and Roughgarden algorithm. So in this landmark paper in 2008, they introduced a polynomial-time algorithm for computing a correlated equilibrium when the representation satisfies two conditions. One is a polynomial type, which means your number of players and number of actions per player are bounded by polynomials in the size of the representation. So the other condition is polynomial exploitation property, which means we have access to a polynomial time algorithm for computing the expected utility given a product distribution, which is a distribution where each player is randomizing independently. In other words, just mixed strategy profiles. So the output of this algorithm is are mixtures of polynomial numbers of product distributions. So since each product distributions can be represented in polynomial number of bits, the output can be represented in polynomial number of bits. So this is a very important result because unlike Nash equilibrium, where computing one Nash equilibrium is generally p-pat complete, this allows us to compute a correlated equilibrium in polynomial time, and it applies to a very wide range of representations, because the representations I mentioned earlier all satisfy these two properties. And if tomorrow you invent a new representation, you don't have to try to find a new algorithm for correlated equilibrium. You just have to find a new algorithm for expected utility, and then you're done. So, I'll give a brief overview of the algorithm, which is based on certain existing proofs of the existence of CE using LP duality in the economics literature. So first, consider the linear program P, which is similar to the feasibility program before, except that instead of x summing to 1, we're maximizing it. So there are two cases. So first, we observe that x equal to 0 is always a solution. So there are two cases. Either that's the only solution, then it's the optimal solution, or there exists other non-zero solutions, in which case we can scale it infinitely, therefore it will be unbounded. But in that case, we can just take a non-zero solution and then scale it to sum to 1, and we have a correlated equilibrium. So therefore, one way to prove the existence of CE is to look at the dual program, which we call D, and if we can prove that D is infeasible, then by LP duality, then the primal will be unbounded, and we're done. So how do we prove that D is infeasible? So they gave this following lemma. For every dual vector y greater or equal to 0, there exists a product distribution x such that this expression is 0. So in fact, this lemma then implies that the dual program is infeasible. Why? This is because x u transpose y is a convex combination of the left-hand side of the D, and therefore, for any feasible y, it's supposed to be less or equal to 1, less or equal to minus negative 1. However, it's equal to 0, therefore, contradiction, there does not exist a feasible y. Furthermore, they show that there exists a polynomial-time algorithm that computes such an x given y. So in this talk, I'm not going to show the proof of this theorem or the details of the algorithm. we're just going to use this as a black box. So, so far this gives a proof of there existed correlated equilibrium, but the proof is not constructive at all. So Papadimitriou and Roughgarden propose a way to make this proof constructive using the so-called Ellipsoid Against Hope method. So basically, we look at we take the dual program D, which has polynomial number of variables and exponential number of constraints, but we recall that although they have exponential number of constraints, if we have a separation oracle, we can just apply the ellipsoid method. And in fact, the previous lemma allows us to construct the following product separation oracle, which, given a set, given a vector y, compute the corresponding product distribution x, and then output this expression as a separation oracle that separates the y from the feasible set. So this, if we use this separation oracle, the ellipsoid method would keep cutting, and the ellipsoid would keep shrinking and would stop after a polynomial number of steps and determine that the program is infeasible. However, we already know that it is infeasible, so how does this help? It turns out that we can make use of the cutting planes that has been generated. So, so we let X to be the matrix whose rows are the generated product distributions, and consider the program D prime, where the constraints are essentially the cutting planes that has been generated by the previous ellipsoid method. So here comes a very important argument, basically saying that if we apply the same ellipsoid method with the same initialization with the following separation oracle, where it returns the ith cut given the ith query. So then it should go through the same sequence of queries and same sequence of ellipsoids and end up having the same result, which is returning infeasible. And therefore, we can conclude that D prime is infeasible, presuming that certain numerical problems do not arise. So in a couple of slides, we'll see what these numerical problems are. So now that it's infeasible, this implies that its dual, P prime, is unbounded. And furthermore, this linear program has polynomial size, so we can solve it in polynomial time. And because it's unbounded, we can find a non-zero alpha vector, and we can then scale it to be a distribution. Then we observe that X transpose alpha satisfies the incentive constraints, because if we group X transpose alpha together, then U times that is greater or equal to 0. So therefore, that gives us a correlated equilibrium. And this is essentially, alpha is a mixture over the rows of X, and each row of X is a product distribution, so the result is a mixture over product distributions, which can be represented compactly. So far, all the operations are just polynomial time operations, except that although the matrix XU transpose is polynomial in size, actually computing it using matrix multiplication would involve exponential number of operations, because the inner dimensions would be exponential. Nevertheless, they observe that the entries are actually just differences of expected utilities under product distributions. And since we assume that we have this algorithm for it, we can compute it in polynomial time. So more serious are the certain numerical issues. Recall that a run of ellipsoid method requires as input an initial bounding ball as well as a volume bound V, where the algorithm would stop once the volume of the ellipsoid goes below V. So in order to correctly prove the infeasibility of an LP, we need to pick the right values of R and V, which then depends on the maximum encoding size of the LP. So if we look at D prime, each constraint of D prime is this convex combinations of existing rows of D. So this may require more bits than any one of the existing constraints of D. So since the resulting encoding size will be bigger, then just running the same ellipsoid method on D prime with the same parameter as the one on D would not be valid, and therefore the infeasibility of D prime is not guaranteed, and the rest of the algorithm would break down. Papadimitriou and Roughgarden in their paper talks about this issue and actually proposed a method to overcome this issue. However, recently Stein, Perillo, Ostagler has showed that there are certain flaws in their argument, and the algorithm as proposed would be insufficient to compute an exact solution. So they furthermore give a kind of slightly modified version that computes an approximate solution efficiently. So what about computing exact CE? So Stein et al. Also showed that if an algorithm satisfies the following properties: one, it computes rational solution; two, it computes convex combinations of product distributions; three, it computes convex combination of symmetric distributions when the game is symmetric. Then there exists a symmetric game such that this algorithm would fail to find an exact solution. So they show this by actually constructing a symmetric game such that the only CE that satisfies 2 and 3 would be irrational. So what this means is that this algorithm, well, the current ellipsoid against hope algorithm falls into this category, but also any algorithm that uses the product separation oracle falls into this category because it would return a symmetric product distribution given a symmetric game and symmetric input. So does this mean that it's hopeless to compute an exact solution? Maybe does this mean that approximation is the best we could do? But on the other hand, we know that there exists exact rational correlated equilibrium given a game with rational inputs. This is because the set of CE is defined by a set of rational linear constraints, and if we just pick a vertex of the resulting polytope, then that must be rational. And in fact, they correspond to basic feasible solutions of the original set of constraints. So furthermore, such a CE would have only a polynomial number of non-zero entries, so they can be compactly represented because they only have polynomial size support. So can we compute this? It turns out that we can, and that's what we propose is a variant of the Ellipsoid Against Hope algorithm that is able to compute the exact rational CE in polynomial time given a representation satisfying the same properties as before. So, so furthermore, the output is a CE that is a vertex of the polytop of CE, which has polynomial size support. And our algorithm is the first algorithm that actually computes a correlated equilibrium with polynomial size support. So why would we want to find such a type of solutions? So one is because these are has a simpler form than the one before, where it's a polynomial number of mixed strategy and profiles. Here it's polynomial number of pure strategy profiles. So it will have a number of advantages, like being easier to sample from and being easier to verify. In fact, given such an equilibrium, you don't actually need to have the expected utility algorithm in order to verify whether it's an equilibrium or not, because it only has polynomial number of probabilities. You can just do it directly. So the key ingredient of our algorithm is the following. Instead of the product separation oracle of the original algorithm, we use a modified version, which we call the Purified oracle, that generates cuts corresponding to pure strategy profiles. In particular, given the input y, it would output basically a row of the original dual program D correspond to some specific action profile S, such that this constraint is being violated at y. So because these are the cutting planes that we use to generate D prime, then each constraint of D prime is from one of the original constraints of D, so the maximum encoding size doesn't increase. Therefore, any one of the ellipsoid method that is valid for D would also valid for D prime. So we no longer have any problems with these numerical issues, and it doesn't require any other mechanism to deal with it. And basically, the rest of the algorithm just runs naturally. And in the end, a solution of P prime is a mixture of polynomial number of pure strategy profile. And we can then, from such a feasible solution, we can get to a basic feasible solution using a standard algorithm, which gives us the vertices of the polytopes. So once we have this pure separation oracle, then the rest of the algorithm follows quite naturally. So for the rest of the talk, I'll talk about how we construct such a pure strategy separation oracle. So the first question would be, does there even exist pure strategy cutting planes? So the answer is yes, and it's actually fairly easy to prove. So given any vector y greater or equal to 0, we can find a pure strategy profile S such that the corresponding row in the dual program is greater or equal to 0. So we can prove by starting with the product distribution X such that X U transpose Y is 0 from the previous lemma. So now we can think of this expression as the expected value of this the rows of D under the distribution X, which we can write it as an expectation. Because this is an expectation, there must be one S such that it achieves values at least as great as the expectation. which is 0. So that basically follows from there. This is kind of a direct application of the probabilistic method, and as is similar to this kind of proofs, this is not efficiently constructive because to find such an S, there exists exponential number of pure strategy profiles. So if we do the intuitive thing and sample from this distribution, then it will only guarantee us an approximate cutting plane after a polynomial number of samples. But that's not really what we want. We want kind of exact solutions. So instead, we propose a derandomization method. In particular, we use the so-called method of conditional probabilities. So I'll go through the separation oracle algorithm. So given a y, at first we compute the corresponding product distribution x satisfying this. Then we go through each players in sequence from 1 to n. So for each player, we pick a strategy such that the conditional expectation remains non-negative. So what is this conditional expectation? It is the same expectation as before, conditioned on the choices we have made so far. So from the player 1 to the current player. So basically, we're replacing the first p player's strategies with pure strategies. So we claim that such p must exist because, kind of by induction, the previous expectation is non-negative, and it starts from 0, so it keeps being non-negative. And so how do we know which one it is? We can actually evaluate each of these conditional expectations by making use of the expect utility algorithm, because they are actually just linear functions of the expected utilities. So in the end, we have we go through every player and we have a pure strategy profile, and we output the corresponding cutting plane. So this entire algorithm can be shown to run in polynomial time. So why does this work? And like, how does this avoid the counterexamples proposed by Stein et al.? Is because we go through each player sequentially, then the result can be asymmetric, even if we start with a symmetric game with a symmetric input. So in fact, this kind of symmetry breaking seems to be necessary, because otherwise it will just run into the existing counterexample. So I'll just conclude. We proposed a variant of the existing algorithm that computes exactly in polynomial time, and the key ingredient is derandomization of the original separation oracle and into a pure strategy separation oracle. And as a result, the rest of the algorithm is simplified, and we have certain other nice properties like polynomial size support. So as one future direction is to look at this as a general method for this kind of ellipsoid against hope method for making certain proofs more constructive. And one example is Huang and Ronstango's paper on polynomial algorithm for a related concept of extensive form Correlated Equilibrium. There we still have the similar type of kind of x u transpose y greater or equal to 0. except that the X is no longer a product distribution. Instead, it's a type of behavior strategy. But our algorithm still works because it doesn't require X to be product distribution. As long as you can still compute the expected or the conditional expected utilities, then this can still be evaluated. Okay. Yeah.
Thank you. One question? A real question, but I think it's the right place to ask it. I mean, if you look at the general game, not the compact game,
okay.
What is the complexity of computing an exact correlated equilibrium? Is it exponential, as the linear programming suggests, or maybe it's a special enough problem that may be less? I keep asking this question for a couple of years, and I never could get an answer. I haven't yet gotten an answer. So again, look at the general. Take an n-person game, say that every player has only 2 strategies. So the number of unknowns is 2 to the power n. Number of inequalities is n squared or something like this. So it's polynomial. So if you look at the LP problem, then it's exponential in n. Nevertheless, I have not yet heard of a proof showing that this is indeed exponential in n, computing the correlated equilibrium. Maybe computing correlated equilibrium is a special problem. For example, here they show that there is some structure that says that it may be an easier problem.
So do you mean whether it's kind of strongly polynomial instead of polynomial, or do you mean whether it's like in the normal form representation, or? But
I think CJ wants to be sublinear in the normal form representation.
I'm asking, or proof that it is indeed as complex as a general linear programming problem as this number of constraints and unknowns.
You want to follow in with n, you know what it is.
That would be very nice to get.
Despite of the fact that exponentially many input items.
Yeah. For example,
okay.
there are nice approximations that don't work for general LP problems. Yes, regret and so on. They give you a nice approximation in polynomial time. Yes, so this is not a general LP problem. There is some structure there. Whether this makes it easier than e to the power n, I don't know. That's the question. So I think it's the right place.
Okay.